And we'll move on now to the last speaker in this session, Natasha Lewinsky, and she's going to move back to fish, and we're going to be reviewing uptake of quantum dots. So over to you, Natasha.
All right, thank you all for staying for my talk. I know I'm in between you and the coffee break, so I'll try to be brief. Today I'll be presenting some results on a dietary exposure study of zebrafish to quantum dots that I conducted in Dr. Rebecca Drezik's group at Rice University. But briefly, I would like to mention that I'm currently a Whitaker Fellow at the Institute of Work and Health in Lausanne, Switzerland, working with Dr. Michael Rittaker, who I thank for sending me to this conference. And I would also like to thank the chairs of the Eco-Hazard Assessment section for allowing me to present my results to you today. So if you remember from the first talk, cadmium-based particles were not in the graph of the large produced nanoparticles. However, if you think about, or you look at what's being commercially produced today in terms of quantum dots, there are 9 companies where you can buy quantum dot solutions, and they're listed at the top of this slide. And one company in particular, Acute Vision, has been working in partnership with Nexus Lighting and Samsung to develop LED-based light bulbs and displays. And in the United States, these array light bulbs are available at common hardware stores for about $9 US per bulb. So they are in the commercial market and could result in a higher potential for environmental release of quantum dots. And so in collaboration with Dr. Vicki Colvin's group at Rice University, I studied quantum dots in zebrafish and Daphnia. And the characterization of the quantum dots that I used is shown on this slide with TEM and DLS measurements, as well as spectroscopy. And all of the quantum dots, which were polymer coated using 2 common polymers used in the life sciences, as well as their PEG or polyethylene glycol counterparts, were found to have hydrodynamic diameters less than 50 nanometers and zeta potentials in the negative region as synthesized. And so the motivation for the dietary exposure study was from a preceding study I did on Daphnia magna, where I looked at the uptake and clearance as well as toxicity of the 4 different coded quantum dots in Daphnia magna. And here I just show some summary of acute toxicity results in the Daphnia, since Daphnia will serve as the food source for the zebrafish. And for all the polymer coatings, I found only one had a LC50 value that was achieved, and this could be due to high body burdens. If you see, I calculated a bioconcentration factor, which was quite high. And this also, I suspect, was due to the particle stability, because the particles tended to aggregate. They would absorb to the Daphnia, and with larger particles, Daphnia can ingest them and retain them more easily, and then lead to this higher body burden. Focusing on the clearance, though, I found that there was, after feeding the Daphnia quantum dots, or exposing the Daphnia to quantum dots at a concentration of 0.6 parts per million cadmium equivalents for 24 hours, and then removing the Daphnia to clean suspensions with either just their synthetic media or synthetic media with clean algae. The amount that was retained after 48 hours of clearance was quite high, between 36 to 53% of the ingested dose. And although I didn't carry out the experiment further, calculating the expected gut passage time, I found this to be about 9 days. And given that the literature says that algae takes about 8 to 24 hours to pass through Daphnia, this is a significant retention and suggests bioaccumulation. And so because of this, I wanted to see, given that the quantum dots could retain in the Daphnia, there's a higher chance of the quantum dots being transferred to higher predatory organisms such as zebrafish. And so I exposed adult zebrafish to 10 quantum dot contaminated Daphnia over a 14-day exposure period. And then for some of the zebrafish, I continued to feed them just normal Daphnia, non-contaminated, for an additional 7 days to look at the clearance pattern. And at every other day time points, I collected 3 zebrafish and imaged and dissect these fish for ICP-MS metal analysis to quantify the quantum dots in the organisms. And so here I show the uptake and clearance as measured by ICP-MS in the zebrafish. And although this uptake model is not the best in terms of fit, using Michaelis-Menten, I found that the saturation concentration was around 7.5 milligrams per kilogram in the adults, which is close to the range that was expected given the amount of quantum dots that was measured to be contained in the Daphnia themselves. So like I said, I controlled the amount that was exposed. There was 10 Daphnia, and so we expected a range of 5.2 to 8.2 milligrams per kilogram. But then the clearance of the quantum dots was a biphasic with a fast clearance in the first 24 hours, followed by a slower clearance over the remaining 6 days. And the elimination rate constant, which is the fraction of the dose eliminated per unit time, was found to be 0.6 per day. And so looking at the clearance a little more closely, we found around 90% of the dose was cleared in the first 24 hours. And after the entire 7 days, around 99% was cleared based on this ICP-MS cadmium quantification. And the gut passage time was calculated to be about 16 hours. And I'm not sure if I said what gut passage time was before, but that's the time to have 90% of the dose eliminated in the organisms. I also calculated the biomagnification factor, which is the concentration of the quantum dots in the predator organism, divided by that in the prey, and I found this to be 0.04. And biomagnification factors of 1 or greater are considered of concern, and so this suggests that there is little or possibly no biomagnification happening in this acute dietary exposure case. I also looked at juvenile zebrafish, so looked at zebrafish that were 2 weeks old and then exposed to quantum dot contaminated Artemia because the mouths of the zebrafish were too small to ingest Daphnia neonates. And I found, looking at their specific growth rates, that the growth didn't seem, at least on a gross evaluation, to be affected, since the rate was similar to that is as shown in literature. And then looking at the uptake and clearance, the uptake was not as steady because I didn't control too much the amount of food, like in the adult study, that the juvenile fish were ingesting. However, if you look at the clearance, which was what I was more interested in, again, you see this biphasic pattern where there was fast clearance in the first 24 hours and then again this slow clearance in the remaining days. And looking at the elimination rate constant, it was similar in the juvenile fish to those in the adults, with a 0.52 fraction per day eliminated. And so just to make a comparison across the 2 types of organisms, I said that the zebrafish study was motivated by the Daphnia study because I found that there was this retention or slowed clearance of the nanomaterials in the Daphnia. However, when you do look at the higher organisms, I found that the clearance was similar to what's found for, say, in the literature you see studies with just cadmium-free metal in Daphnia fed to zebrafish, and so this is a not different clearance, and since the fish are expected to clear in about 8 to 24 hours, again, like the Daphnia, the gut passage time of 16 hours doesn't suggest a slowed clearance, and therefore it could just be passing through. If you think about the question that was asked to the first speaker about whether or not there's a food chain effect. And so just to sum up my talk, just some brief points. The Daphnia were found to bioaccumulate the quantum dots, and in the zebrafish, while there's trophic transfer of the quantum dots from the Daphnia to the zebrafish, there was no biomagnification expected, at least from the results that I found. And so I would like to acknowledge all of the people that helped me generate these results, particularly my old advisor, Rebecca Drezick, as well as Dr. Vicki Colvin and Dr. Daniel Wagner for helping me with the resources on this. I'd also like to acknowledge the funding sources, particularly CVIN and NSF, and then for me to be presenting here, the Whitaker Foundation and IST. And for more information about the results I presented, you can look at the 2 publications that are listed at the bottom of this slide. And thank you for your attention.
Okay, well, thank you very much, Natasha. And do we have any questions from the audience?
More, I tell you what, this university leads more of a comment than a question. Very nice study, that's a lot. My colleague, Professor Alan, has done something similar with nematodes, where he's engineered them to green fluoresce if you get a toxic response in the digestive tract. And so he has studied similar ranges of quantum dots to yourself, and it might be interesting to compare some of his results with nematodes with yours. Okay. I don't know if there's any scope for engineering some green fluorescent Daphnia, but that might be fun too. To
or maybe the zebrafish,
yes. Insects. Thank you so much.
Thank you.
Hi, very nice talk. Just a question about your uptake clearance study.
Yes.
Did you take confocal images after the uptake and clearance had occurred, or did you just analyse ICP-MS? The question is being, did you determine that quantum dots had left by the cadmium clearance, and did you actually study whether or not the cadmium can be leached from the core and the quantum dots are actually still inside?
So I didn't study that in too much detail. However, I did both, and I haven't shown it here, but I did whole organism imaging for fluorescence using a Maestro imaging system to see if the quantum dots were still retained, but the sensitivity of the machine is low. And then I also tried to section the gut, but to not use too many organisms, I tried to focus more on quantifying the amount because I couldn't use fluorescence to necessarily quantify the amount of quantum dots that were in there. But from the imaging I did, I can't answer whether or not there was a breakdown, but the fluorescence was reduced, so that suggests that at least the crystal was not as intact because it was harder to find than at the beginning of the experiment versus as you went along towards the end. Thank you.
Hello. Yeah. Okay. Well, in Europe, cadmium is, I think, in principle, it's prohibited in electronic products, and I think there's a temporary exemption for the use in light-emitted diodes. So I'm interested to know: do you really think that we will see quantum dots released from the lamps and distributed in the environment? Do you think that's a realistic? Or is it more a question of release of cadmium into the environment?
I think it may be both. Again, as one of the speakers said yesterday, the likeliness of materials embedded or deposited on a surface to release is lower. But then if you also just think about the production method, and so my understanding of the electronics industry is not that much, but I'm sure you have to tailor the type of particle to get the effect that you want. At least to get the size selected emission wavelengths for biomedical purposes, you need to have a monodispersed solution. And so then if you think about how much would be produced, and I'm sure they will find a way to upscale. I'm sure there's plenty of chemical engineers working on large-scale production of these particles, that then the waste, okay, it's cadmium, so it'll go to hazardous waste. But my understanding of hazardous waste disposal is that that's a whole nother story in terms of leaching from landfills, and then where does this leachate go? And again, we're going outside of the scope of my knowledge, but I think there is, not in the near present, but some type of potential exposure. And then it's just more, do you want to focus on just the quantum dots, or think about nanoparticles?